Section: Introduction. In this section, we explore denoising diffusion models, which are used to create synthetic images by gradually removing noise from an initial noisy image. The key component of these models is a neural network that acts as the denoiser, helping to reveal the final image step by step. The denoising process can be mathematically represented as solving a differential equation, either ordinary or stochastic, with various parametrizations and solvers being considered. To ensure the generated images meet certain criteria, such as being aligned with a specific class label or text prompt, the denoiser is conditioned accordingly during training. The goal of training a diffusion model is to cover the entire data distribution, which can be challenging when dealing with low probability regions. Classifier-free generation has become a common approach to focus on generating images from high probability regions, improving prompt alignment and image quality. However, there are limitations to classifier-free generation, such as being restricted to conditional generation and potential issues with sampling trajectory alignment. To address these challenges, we introduce a new method called auto, which separates the image quality improvement effect from prompt alignment. By using a simplified version of the main model as a guide, we avoid task discrepancies and achieve better control over the generation process. We validate the effectiveness of our auto method through various tests and practical image synthesis scenarios, including class conditional and text conditional settings. Our method also allows for unconditional image synthesis. Quantitative tests show significant improvements in generated image distributions, setting new benchmarks in image generation metrics. We plan to release our implementation and pre-trained models for public use. Section Summary. In this section, we summarize the concept of denoising diffusion models, which generate images by gradually denoising noise through a neural network denoiser. These models aim to cover the entire data distribution, but struggle in low probability regions, leading to the development of classifier-free generation, CFG, to focus on high probability areas. However, CFG has limitations, prompting the introduction of a new method called auto, which improves image quality by using an inferior version of the main model as a guide, leading to enhanced image synthesis results. Section: Classifier-free guidance. In this section, we explore how classifier-free guidance, CFG, can enhance image quality in complex visual datasets. When generating images, finite capacity networks may introduce errors that result in less clear images compared to the training set. CFG, a common technique, adjusts the generated samples to align more closely with the class label, prioritizing canonical images over diverse ones. In a diffusion model with two denoiser networks, denoted as 46 and 47, the guidance is achieved by blending the results of these denoisers with a factor of 10. By adjusting this factor, we can control the influence of each denoiser on the final output. This guidance allows us to access the score of the implied density, which can impact the likelihood of a sample belonging to a specific class. In CFG, we train an auxiliary denoiser to refine the distribution marginalized over a class label, which helps guide the image generation process towards the desired class. However, solving the diffusion ode with the score function does not directly follow the specified density, leading to potential issues like distorted sampling trajectories and mode dropping. Despite these challenges, CFG often leads to significant improvements in image quality. To understand why CFG enhances image quality, we investigate a 2D toy example where a small-scale denoiser network is trained on a synthetic dataset with specific characteristics resembling realistic image manifolds. We observe that unguided diffusion models can produce unrealistic outliers, while CFG helps mitigate this issue by aligning the samples more closely with the data distribution. In summary, CFG improves image quality by guiding the image generation process towards the desired class, addressing issues related to outliers and unrealistic samples that may arise in unguided diffusion models. Section Summary. In this section, we explore how classifier-free guidance, CFG, enhances image quality by guiding image generation towards more realistic outcomes. By training an auxiliary denoiser network to denoise the distribution marginalized over a specified class label, CFG helps align generated images with the desired class. This approach improves image quality by preventing outliers and unrealistic samples that can arise from unguided diffusion models, ultimately leading to more accurate and visually appealing results. Section: CFG eliminates outliers. In this section, we demonstrate the impact of using classifier-free generation, CFG. When we apply CFG during generation, we notice that the generated samples stay away from the class boundary, avoiding the gray area completely. Entire sections of the distribution are also removed. Additionally, we observe that the samples are pulled towards the center of the data manifold, away from low probability regions. This helps in getting rid of unlikely outlier samples, leading to an improvement in image quality. Boosting the class likelihood alone cannot explain this increased concentration. We believe that this phenomenon arises from a quality gap between the denoiser networks used. One denoiser has a more challenging task as it needs to generate samples from all classes simultaneously, while the other can focus on one class for each sample. The denoiser facing the tougher task may not fit the data as well due to limited training resources. This difference in accuracy is evident in the learned densities plots. CFG not only boosts the likelihood of a sample belonging to a specific class but also enhances the likelihood of coming from a higher quality implied distribution. We introduce an additional force that pulls the samples towards higher values based on a specific equation. By plotting this ratio for a toy example, we observe that the ratio decreases as we move away from the data manifold. The gradients point towards the data manifold, concentrating the samples there. Each contour of the density ratio represents the likelihood that a hypothetical classifier would assign to a sample being drawn from one distribution instead of another. By pushing samples towards the good side, we concentrate them at the data manifold. We anticipate that the two models may struggle to fit certain areas, but to varying extents. The disagreement between the denoiser's predictions will be more pronounced in these regions. CFG acts as an adaptive truncation method that identifies underfit samples and guides them towards better samples. While the truncation may overshoot the correction, resulting in a narrower distribution than the ground truth, it does not negatively impact the images. In contrast, a naive truncation approach would lead to less varied, oversimplified images. Our method involves guiding a high-quality model with a lower-quality model trained on the same task and data but with certain degradations. We call this procedure auto. In our 2D example, using a smaller model with fewer training iterations successfully pulls the samples closer to the distribution without dropping any part of it systematically. Auto aims to reduce errors made by the stronger model by comparing it to the weaker model's predictions and making adjustments. This approach works well when the two models suffer from compatible degradations. Choosing a weaker model that exacerbates these degradations can lead to improved results. Section Summary. In this section, we demonstrate that classifier-free generation, CFG, eliminates outliers and improves image quality by pulling samples towards the core of the manifold and away from low probability regions. By guiding a high-quality model with a poorer model trained on the same task, conditioning, and data distribution, we observe that this technique, called auto, effectively reduces errors made by the stronger model towards better samples, especially in regions where both models disagree. Section: Study on synthetic degradations. In this section, we conducted a study on synthetic degradations. We wanted to confirm our idea that both models would be affected by similar types of degradations. To test this, we carried out an experiment where we introduced artificial corruptions to a well-trained image diffusion model. By adjusting the level of corruption, we created two networks, 53 number 53 and 52 number 52, based on the original model. This setup allowed us to compare the impact of different levels of corruption on these networks while using the untouched original model as a reference point. We observed that when the degradations were compatible, the auto process was able to largely reverse the damage caused by the corruptions. For the base model, we used the EDM2S model trained on ImageNet 512 without dropout. We then created Network 53 number 53 by adding 5% dropout and Network 52 number 52 by adding 10% dropout to the base model. Through the auto process, we achieved the best result with Network 83 number 83, matching the performance of the base model. Additionally, we introduced input noise by increasing the noise level by 10% for Network 53 number 53 and 20% for Network 52 number 52. Again, using the auto process, we obtained the best result with Network 84 number 84, matching the base model's performance. When we mismatched the degradations by applying dropout to one network and input noise to the other, we did not see any improvement in the results. In such cases, the best performance was achieved by disabling one network and using the less corrupted network exclusively. While this experiment supported our initial hypothesis, we do not recommend using these synthetic degradations in practical scenarios as real-world diffusion models do not typically suffer from these specific types of degradations. Moving on to the results, we evaluated our approach using ImageNet at resolutions of 16 number 16 and 15 number 15. We used the EDM2 model as our baseline and explored variations such as EDM2S and EDM2XXL with different sampling parameters. By introducing degradations like shorter training time and reduced capacity in the guiding model compared to the main model, we achieved the best results. We also optimized the weight and EMA length parameters for the EDM2 networks using grid search. Our method significantly improved FID and FDDI-NOV2 metrics. For instance, with the small model, EDM2S, in ImageNet 512, our approach outperformed existing methods and set a new record for this dataset. The results were even better with the largest model, EDM2XXL. In ImageNet 64, we achieved new records for FID and FDDI-NOV2 metrics. Notably, our approach can also be applied to unconditional models, enhancing the quality of generated images. Overall, our method shows promising results in improving the performance of diffusion models across different datasets and model sizes. Section Summary. In this section, we conduct a study on synthetic degradations to validate our hypothesis that different models must experience similar types of degradations. By applying controlled synthetic corruptions to a well-trained real-world image diffusion model, we create main and guiding networks with varying levels of corruption. Our experiments show that when degradations are compatible, an auto method can effectively mitigate the damage caused by these corruptions, aligning the performance of the corrupted models with the untouched base model. Section: Ablations. In this section, we experimented with different setups to understand how they affect the performance of our models. We found that having separate exponential moving average (EMA) lengths for the main and guiding models is beneficial. When both models were forced to use the same EMA length, the Frechet inception distance (FID) metric worsened. We also looked at the impact of degradations like reduced training time and capacity on the models. We observed that reducing the training time and capacity of the guiding model had a significant effect on the FID metric, with most of the improvement coming from reducing the training of the guiding model. We also explored the sensitivity of our models to various hyperparameters. We found that training the guiding model around 1/8 as much as the main model yielded the best results. Having the training budget also performed well, while doubling the training compromised the results. The choice of weight and the capacity of the guiding model also played a role in the model's performance. We found that reducing the capacity of the guiding model to XS gave the best results. Additionally, we investigated other degradations for the guiding model but did not find them to be beneficial. For example, reducing the amount of training data for the guiding model did not improve results. Applying noise on top of our method reduced its benefits, indicating that noise is helpful at all levels. Deriving the guiding model from the main model using synthetic degradations did not work well, emphasizing the importance of aligning the degradations between the two models. In terms of qualitative results, we compared our method with a standard method, CFG, in generating images for ImageNet 512. While both methods improved the quality of images as the weight increased, our method produced a wider range of image compositions compared to CFG. Our method also showed better coverage of training data, resulting in lower FID scores. We further applied our method to a large-scale image generator, IF, and compared it with CFG. Our method preserved the style and visual complexity of the images better than CFG, which tended to simplify the images towards a canonical depiction. By combining both methods, we aim to provide a new artistic control for generating images. Section Summary. In this section, we explore various ablations to understand the impact of different factors on the performance of our method. We find that allowing independent exponential moving average (EMMA) lengths for the main and guiding models is beneficial, with a majority of the improvement coming from reduced training of the guiding model. Additionally, our method outperforms the standard CFG in terms of Frechet inception distance, FID, and produces a wider range of image compositions compared to CFG, which tends to head towards a more limited set of canonical images per class as the weight increases. Section: Discussion and Future Work. In this section, we have demonstrated that by going classifier-free, we can combine various factors and explore a whole new design space with a fresh perspective and simple adjustments. By eliminating the unnecessary ties to conditioning, we can achieve significantly improved outcomes. Our future research may involve formally establishing the conditions under which auto can be advantageous and developing practical guidelines for selecting the most suitable guiding model. Our proposal, which involves using a smaller model early on, is theoretically feasible but not currently feasible for large-scale image generators. These generators are typically trained in multiple stages, potentially leading to changes in the training data and distribution shifts between snapshots, which could contradict our assumptions.